Welcome back to the second part of the M25 AAHL Paper 1 Time Zone A walkthrough. We are now looking at question 6 concerning the equation of lines in R3. You are given the equation of two perpendicular lines, and you are also given that they intersect at a unique point. You are then asked to find the value of A and the value of B. So let's get started. We know the two lines are perpendicular. The two lines are perpendicular if the dot product of the direction vectors is equal to 0. So 0, A, 1, dot 1, 2, 3 is equal to 0. Thus 2A plus 3 is equal to 0. And we can find the value of A. To find the value of B, we will need to find the point of intersection. To do that, we'll just write out the most general form of any point on the line. So any point on the line L1 will have the coordinates 4, A lambda, and -1 plus lambda. Any point on line L2 will have coordinates 1 plus mu, 2 mu, and -b plus 3 mu. They intersect when the x, y, and z coordinates are equal. In other words, this has to be true. From the first equation, we deduce mu is equal to 3. From the second equation, we find that A is equal to -3/2 times lambda is equal to 2 times 3. So lambda is therefore -4. Plug mu and lambda into the third equation, we would get -1 minus 4 is equal to -b plus 9. Or b is equal to 14. Thus, A is equal to -3/2, and B is equal to 14. Moving on to question 7, you are given the complex number z is equal to 3 to the power of I minus 1. We know that we cannot work with a complex number in this form, so we gotta convert it to the form e to the power of something I, which is the direction that the IB is nudging us towards. Part A is surprisingly straightforward. Write the integer 3 in the form e to the a. Well, 3 is going to be e to the length 3. Done. B. Hence, give your answer in the form p cos ln of q. Find the real part of z. Okay, so let's use the answer to part A, shall we? If z is equal to 3 to the power of I minus 1, 3 is e to the power of ln 3 times I minus 1. So that's going to be e to the I times ln 3 times e to the negative ln 3. E to the negative ln 3, that's 1/3. The real part of z is simply 1/3 times cos of ln 3. The second part of the question concerns the complex number 1 over z. 1 over z is therefore 1 over e to the ln 3 of I minus 1, which is e to the negative ln 3 of I minus 1, which is e to the I ln of 1/3 plus ln 3, which is e to the ln 3 times e to the I ln of 1 by 3. E to the ln 3 is simply 3. E to the I ln 1 by 3, that would be cos of ln 1 by 3 plus I sine of ln 1 by 3. Thus, the real part of 1 over z is therefore 3 times cos of ln 1 by 3. Question 8 of the paper is an induction question. In part A, we are asked to show that 1 plus log base 2 of n is greater or equal to log base 2 of n plus 1. So we will start with the left-hand side. 1 is the same thing as log base 2 of 2. Now we're just adding two logarithms with the same base. We multiply the arguments. Since n is a positive integer, we know that n is greater or equal to 1. If we plus n to both sides of the equation, we will get 2n is greater or equal to n plus 1. Thus, log base 2 of 2n is greater or equal to log base 2 of n plus 1. The log function is increasing for O n. Part B. Now we are asked to use mathematical induction to prove that Sima's claim is valid. So let's start with a base case. When n is equal to 1, the left-hand side is equal to 1. The right-hand side is log base 2 of 1 is equal to 0. 1 is greater than 0. Therefore, the base case is true. We'll now assume that it is true for n equals to k. In other words, we're assuming that k is greater than log base 2 of k. This is also called the induction hypothesis. And we are now considering the case n equals k plus 1. So let's start with the left-hand side. K plus 1 is greater than log base 2 of k plus 1. We are making use of our induction hypothesis here. This guy is greater or equal to log base 2 of k plus 1, using our result from part A. However, for what value of k is this true? The equal sign only occurs when k is equal to 1. However, we proved that the base case is true, and now we're assuming the statement holds true for any value of n, which is greater than 1. Thus, log base 2 of k plus 1 is strictly greater than log base 2 of k plus 1. Hence, we just proved that k plus 1 is greater than log base 2 of k plus 1, which is to say, our statement holds for n equals k plus 1. Thus, we now have to write our conclusion. By principle of mathematical induction, if the statement is true for n equals to k, we proved that it is true for n equals k plus 1. We also proved that it is true for n equals to 1, thus the statement is true for all positive integer values of n. The conclusion is box standard. You can use this conclusion, or you can use the conclusion that can be found in the mark schemes. Just memorize it and put it on the exam. That way, you know that you always get that final R1. This is question 9 on AAHL Paper 1, Time Zone A. We have a homogeneous differential equation, and we are also given that y is equal to 0 when x is equal to 2. Using a substitution y is equal to vx, we are asked to show that x squared minus 2xy minus y squared is equal to 4. So let's get started. This is a book standard question. If y is equal to vx, the y over dx is gonna be v prime times x plus v. Recall that v is a function of x, so we must use the product rule here. dy over dx is also equal to x minus y divided by x plus y. Dividing both the top and the bottom by y, we will obtain this equation, which we can then use to express it in terms of v. Equating the two, dv over dx times x plus v is equal to 1 minus v over 1 plus v. I am gonna isolate this term. And now we're going to solve this equation using separable variable. I don't like to deal with a negative sign downstairs, so I'm going to multiply both sides of this equation by -1. Now we'll integrate. This integral over here can be found using a simple substitution. You can even read off the value of the integral. The right-hand side is negative ln of x plus c. We know that x is positive, so we can remove the absolute value sign over here. We are also going to replace v with y over x. When x is equal to 2, y is equal to 0. Ln of 1 is equal to 0. So c is equal to ln of 2. Now we have to remove the absolute value sign of the term on the left-hand side. Multiply both sides by 2, As with most differential equations, the hardest part is in the algebra. Exponentiate both sides. On this side, we will have 4 over x squared. And we can see the answer appearing in front of us. Multiplying both sides of the equation with x squared. And there lies your final answer. As requested. This is just a very long procedure. You got to be mindful of the modulus sign over here when removing it. But yeah, that's the end of section A.